Okay, talking about the radical ring. The radical coordinate ring, the third and final ring of information of the unit circle. We've been down this road. We've seen degrees around the unit circle. We've seen radians around the unit circle. We've got a degree ring. We've got a radian ring. Got it. I'm wondering, what the heck is it good for? Patience, grasshopper. That's what we're talking about today. So let's get after this right away and show you what's happening. First of all, this is just the first quadrant of the unit circle. So we're focusing on the first quadrant only. You'll find that all of these points that we're talking about are just reflections over the x or y coordinate, over the x or y axis, to arrive at the other coordinates of the unit circle. So I want you first of all to think about the unit circle as not a circle. I want you to think about the unit circle as a collection of special right triangles, each with a hypotenuse equal to 1. Now we know that there are only two types of special right triangles that we have spoken about. A 30-60 right triangle. So a 30-degree angle is a radian measure of pi over 6. And with a hypotenuse equal to 1, we can find the other two legs of that special right triangle are equal to root 3 over 2 and 1/2. A second special right triangle we have, there's a hypotenuse equal to 1, is a 45-45 right. We know the corresponding radian measure to 45 degrees is pi over 4. And when we do the math here, we can find that the side lengths, the leg lengths of that 45-45 right triangle are root 2 over 2, comma, root 2 over 2. The two legs have length root 2 over 2. Finally, and although this is the same triangle as the 30-60 right triangle, this is a 60-30 right triangle. And we're going to find the two leg lengths are identical. This corresponds to radian measure pi over 3, and I get a short leg of 1/2 and a long leg of root 3 over 2. All right, so we're going to look at those red triangles. They're going to help us arrive at these radical coordinates. What's a radical? Like a square root. So when I say radical coordinates, I'm talking about coordinates most which contain a square root number. And, you know, we're talking about special right triangles that lie within the unit circle. So all these triangles have a hypotenuse equal to 1. Another point of emphasis here. So let's talk about this 30-60 right triangle and place it on the unit circle. And it's 30 degrees or pi over 6. And I'm just going to steal information from the red triangle above to figure out what this coordinate is. Using the red triangle above, I know if I start at the origin and plot that ordered pair, I got to go right root 3 over 2 and up 1/2. And so I have the coordinate for the 30-degree angle measure, or the coordinate for the radian measure, pi over 6. Let's keep trucking. Here's a 45-45 right triangle. Remember, it has hypotenuse equal to 1. And the corresponding radian measure to 45 degrees is pi over 4. And again, using the red triangle above, you may be able to discern what the ordered pair is associated with that. How far right from the origin and how far up do I have to go to land this point on the unit circle? You probably had guessed this correctly. The ordered pair associated with 45 degrees or pi over 4 is root 2 over 2, comma, root 2 over 2. So sitting pretty here. Finally, sticking with the first quadrant, here's this 60-degree angle, the 60-degree angle, which corresponds to pi over 3 in radians. And now I'm looking at the red triangle above and trying to discern from the origin how far do I need to go right and how far do I need to go up to describe that ordered pair. Oh, there's a real simple one, by the way. If I've got a radius of the unit circle of length 1, that's going to be the ordered pair 1, 0. No radicals there. But again, still working on, this is the ordered pair 0, 0. That is the origin. And now, doing this for a reason. If I go on top of the unit circle where that green line strikes, and I drop a line straight down, like I'm going fishing, and X marks the spot, and I know I land right there. This helps me with a nice visual about what the ordered pair should be. I mean, if I were to ask a second grader, you see that X in the middle of the 2 red dots? Yeah. Well, what fraction of the way do you think it is between the 2 dots? I don't know, right in the middle. Well, that kid would be right. In order to plot this point on top, I got to go half unit right, and the one that's more complicated, root 3 over 2 on top. But I see that's just the reverse of the 30-degree radical coordinate. So although this information seems complicated, and there's a lot of different memory tricks that students attempt to use in order to memorize these, in my estimation, the 45 degree, it makes sense that 45 is right in the middle of 90, that the X and the Y coordinates will be identical. I'm going right root 2 over 2 and up root 2 over 2, and most students don't have any trouble remembering that one. And then a lot of errors I see made with the other ordered pair. They don't know what belongs where, and they try memory tricks. I think it's super simple, especially if you start at that 60-degree triangle, to drop a fishing line straight down and know that the X coordinate there is 1/2, which dictates the other one is root 3 over 2. And that just leads me to the 30-degree or pi over 6 angle. I just reverse that and get root 3 over 2 comma 1/2. So it's more of a strategy of location sense than funny memory tricks for those ordered pairs. Doesn't surprise you, I'm going to plot one more at 0, 1 on top there. Okay? I sort of really haven't answered the question, so how is this useful? Well, you guys have been down the road and studied trigonometry with sine and cosine and tangent. We're really going to focus our attention on sine and cosine, but I'm going to emphasize a word here with these descriptions. Sine is defined as opposite over hypotenuse, and cosine is defined as the adjacent side over the hypotenuse. Well, the hypotenuse is equal to 1 here if I'm working these triangles. The hypotenuse is equal to 1. This makes these things pretty clean as I contemplate trigonometric functions as they exist on the unit circle. I don't know what you're getting at. Well, look, here's a unit circle with all 3 rings of information. Yeah, we've built this unit circle from the ground up. We know about degrees and radians and now radical coordinates. And you can see those radical coordinates from the first quadrant, how they are reflected over the x or y axis to arrive at radical coordinates for quadrants 2, 3, and 4. But what is amazing here is we're able to discern the usefulness of the unit circle contemplating the trigonometric functions, the trigonometry, especially associated with cosine and sine, without a calculator. Here comes 4 examples for you. Find the cosine of pi over 3. What are you talking about? I'm just going to put this on my calculator in radian mode, right? No, I got a unit circle. I got pi over 3 on my unit circle. Check this out. For each ordered pair, x and y, on the unit circle as I cruise around the unit circle, the x coordinate corresponds to the cosine of the angle measure you're talking about, whether it's in degrees or radians, and the y coordinate corresponds to the sine of the angle measure, whether you're talking about degrees or radians. So how am I going to do this? I'm talking about the cosine of pi over 3. I locate pi over 3 on the unit circle. There it is. And remember, I want the cosine. Well, these are alphabetized, right? X comes before y alphabetically. Cosine comes before sine alphabetically. So make sure you keep them straight alphabetically. That should be pretty easy. Okay? So I'm looking at, I don't know whether to steal the x or the y. Well, if I want the cosine, I need to steal the x coordinates right there. So as I look at this problem, the cosine of pi over 3 is equal to 1/2. Now you ought to be able to yank out your calculator at this point. Make sure you're in radian mode and put in the cosine of pi over 3, press enter. You should get 1/2. 4 examples total. Take a look. Example 2. Find the sine of 120 degrees. Now I'm shifting gears on you. Now we're in degree mode. Well, the same strategy still exists. I find 120 degrees on the unit circle. 120 degrees on the unit circle, and there it is. Now I ask myself, do I want to steal the x coordinate or the y coordinate here? Well, you know as well as I do, when I go cosine sine, x and y, x comes before y, and cosine comes before sine. The sine is the y coordinate. So at that 120 degrees, I'm going to steal the y coordinate there. It's equal to root 3 over 2. It's equal exactly to root 3 over 2. Can you imagine this? Someone says, hey Johnny, what's the sine of 120 degrees? You go, root 3 over 2. Pretty impressive. With a calculator tied behind your back. Now you ought to be able to take your calculator, put it in degree mode, go sine of 120, and of course it won't spit out on the screen root 3 over 2, but it will put the decimal equivalent to root 3 over 2, which is like 0.866, something like that. I encourage you to give that a test run. So we're shifting up radians and degrees on you guys here on purpose. Let's look at example number 3. I want to now find the sine of 3 pi over 2, the sine of radian measure 3 pi over 2. See if you can do that in your mind's eye before I get going. What am I doing? I'm finding 3 pi over 2 on my unit circle. I'm looking at the ordered pair associated with 3 pi over 2. I'm stealing the y coordinate and getting -1. There's 3 pi over 2. There's -1. I know this answer is -1. Again, take your calculator, change it to radian mode. Be careful if you're working Desmos. And evaluate the sine of 3 pi over 2. That will equal -1. If you landed that plane, that will equal -1. Last example. This time I want to find the cosine of 225 degrees. You know, the real trick of the trade here is, yeah, I can do these, Yeah, can you come up with a unit circle on your own? Can you just sketch a circle, figure out where 225 degrees is located on that unit circle, and write down the ordered pair associated with 225 degrees? Because that's where you need to go. It's not like you're going to have this unit circle laid out in front of you that you can access as a tool. So I'm finding 225 degrees, which is right there. The cosine is asking me, all right, do I want to steal the x or the y coordinate? Cosine comes before sine, x comes before y. Well, the truth is both the x and the y coordinates here are identical, negative root 2 over 2. So when I find the cosine of 225 degrees, I should get negative root 2 over 2. Again, on your calculator, if you put that calculator in degree mode and evaluate the cosine of 225 degrees, you should get negative 0.71, I think is the decimal equivalent to negative root 2 over 2. Okay, so here's a real advantage and where it comes into play with regard to knowing that unit circle. And we tell our students, you got to know that unit circle before you go into trigonometry and calculus, forward, backward, inside out, and upside down. You got to be able to snap your fingers and know where these degree and radian measures are and the radical coordinates associated with each. Then you're going to be sitting in butter. And I also tell my calculus students and future calculus students, if you don't know that unit circle, and the best you can do is a 5 on the AP exam, I feel like the very best you can do is a 3 on the AP exam, unless you know that unit circle. Again, forward, backward, inside out, and upside down. Gotta know it. So make sure you don't spend token time with it. I know for myself as a high schooler, my instructor spent a day on this, and then we were asking and answering questions about the unit circle, and I didn't know the top from the bottom. So I hope we've discussed this in depth so that you can answer questions and know exactly where answers are coming from associated with the unit circle. One last point of emphasis before I fly. That is, you talked a big game with sine and cosine. What about tangent? How does tangent come into play? Well, there's a trigonometric identity that tangent is defined as sine over cosine. So on the unit circle, if tangent is defined as sine over cosine, I can also find the tangent by taking the y coordinate and dividing the x coordinate, y divided by x. So when you see tangent questions associated with the unit circle, you'll go to the radical coordinate you're talking about and take the y coordinate and divide it by the x coordinate. Y divided by x will give you tangent, so that we're not ignoring that. But the tangent functions just aren't, they don't pop with clarity like the cosine and sine functions do. Okay, you guys, that's the name of the game, unit circle, all 3 rings. Take time and get it right. See you later. Over and out.